This command displays the execution plan that the PostgreSQL planner generates for the supplied statement. The execution plan shows how the tables referenced by the statement will be scanned by plain sequential scan, index scan, etc. And if multiple tables are referenced, what join algorithms will be used to bring together the required rows from each input table. The most critical part of the display is the estimated statement execution cost, which is the planner's guess at how long it will take to run the statement, measured in cost units that are arbitrary, but conventionally mean disk page fetches. Actually, two numbers are shown, the startup cost before the first row can be returned, and the total cost to return all the rows. For most queries, the total cost is what matters, but in contexts such as a subquery in exists, the planner will choose the smallest startup cost instead of the smallest total cost, since the executor will stop after getting one row anyway. Also, if you limit the number of rows to return with a limit clause, the planner makes an appropriate interpolation between the endpoint costs to estimate which plan is really the cheapest. The analyze option causes the statement to be actually executed, not only planned. Then actual runtime statistics are added to the display, including the total elapsed time expended within each plan node in milliseconds, and the total number of rows it actually returned. This is useful for seeing whether the planner's estimates are close to reality. Important: keep in mind that the statement is actually executed when the analyze option is used, although explain will discard any output that a select would return. Other side effects of the statement will happen as usual. If you wish to use explain, analyze on an insert, update, delete, create table as, or execute statement without letting the command affect your data, use this approach. Begin, explain, analyze, roll back. Only the analyze and verbose options can be specified, and only in that order, without surrounding the option list in parentheses. Prior to PostgreSQL 9.0, the unparenthesized syntax was the only one supported. It is expected that all new options will be supported only in the parenthesized syntax. Parameters: analyze. Carry out the command and show actual runtimes and other statistics. This parameter defaults to false. Verbose. Display additional information regarding the plan. Specifically, include the output column list for each node in the plan tree, schema qualify table, and function names. Always label variables and expressions within their range table alias, and always print the name of each trigger for which statistics are displayed. This parameter defaults to false. Costs. Include information on the estimated startup and total cost of each plan node, as well as the estimated number of rows and the estimated width of each row. This parameter defaults to true. Buffers. Include information on buffer usage. Specifically, include the number of shared blocks hit, read, dirtied, and written, the number of local blocks hit, read, dirtied, and written, the number of temp blocks read and written. A hit means that a read was avoided because the block was found already in cache when needed. Shared blocks contain data from regular tables and indexes. Local blocks contain data from temporary tables and indexes, while temp blocks contain short-term working data used in sorts, hashes, materialized plan nodes, and similar cases. The number of blocks dirtied indicates the number of previously unmodified blocks that were changed by this query, while the number of blocks written indicates the number of previously dirtied blocks evicted from cache by this backend during query processing. The number of blocks shown for an upper-level node includes those used by all its child nodes. In text format, only non-zero values are printed. This parameter may only be used when analyze is also enabled. It defaults to false. Timing. Include actual startup time and time spent in each node in the output. The overhead of repeatedly reading the system clock can slow down the query significantly on some systems, so it may be useful to set this parameter to false when only actual row counts and not exact times are needed. Runtime of the entire statement is always measured, even when node-level timing is turned off with this option. This parameter may only be used when analyze is also enabled. It defaults to true. Format. Specify the output format, which can be text, XML, JSON, or YAML. Non-text output contains the same information as the text output format, but is easier for programs to parse. This parameter defaults to text. Boolean. Specifies whether the selected option should be turned on or off. You can write true, on, or 1 to enable the option, and false, off, or 0 to disable it. The Boolean value can also be omitted, in which case true is assumed. Statement. Any select, insert, update, delete, values, execute, declare, or create table as statement whose execution plan you wish to see. Outputs. The command's result is a textual description of the plan selected for the statement, optionally annotated with execution statistics. Section 14.1 describes the information provided. Just a few notes. In order to allow the PostgreSQL query planner to make reasonably informed decisions when optimizing queries, the PG statistic data should be up to date for all tables used in the query. Normally, the AutoVacuum daemon will take care of that automatically. But if a table has recently had substantial changes in its contents, you might need to do a manual analyze rather than wait for AutoVacuum to catch up with the changes. In order to measure the runtime cost of each node in the execution plan, the current implementation of explain, analyze adds profiling overhead to query execution. As a result, running explain, analyze on a query can sometimes take significantly longer than executing the query normally. The amount of overhead depends on the nature of the query, as well as the platform being used. The worst case occurs for plan nodes that in themselves require very little time per execution, and on machines that have relatively slow operating system calls for obtaining the time of the day. The notion of functional dependencies is used to define second and third normal form, and the Boyce-Codd normal form, or BCNF. Functional dependencies are fundamental to the process of normalization. Functional dependency describes the relationship between attributes, like columns in a table. Functional dependency, or FD, is a set of constraints between two attributes in a relation. Functional dependency says that if two tuples have same values for attributes a1, a2, up until an, then those two tuples must have same values for attributes b1, b2, up until bn. Functional dependency is represented by an arrow sign, that is x arrow sign y, where x functionally determines y. The left-hand side attributes determine the values of attributes on the right-hand side. Armstrong's axioms. If F is a set of functional dependencies, then the closure of F, denoted as F+, is the set of all functional dependencies logically implied by F. Armstrong's axioms are a set of rules that, when applied repeatedly, generates a closure of functional dependencies. Reflexive rule. If alpha is a set of attributes and beta is subset of alpha, then alpha holds beta. Augmentation rule. If A arrow sign B holds and Y is a tribute set, then AY arrow sign BY also holds. That is, adding attributes and dependencies does not change the basic dependencies. Transitivity rule. Same as transitive rule in algebra. If A arrow sign B holds and B arrow sign C holds, then A arrow sign C also holds. A arrow sign B is called as a functionally that determines B. Trivial functional dependency. Trivial. If a functional dependency fd x arrow sign y holds, where y is a subset of x, then it is called a trivial fd. Trivial fds always hold. Non-trivial. If an fd x arrow sign y holds, where y is not a subset of x, then it is called a non-trivial fd. Completely non-trivial. If an fd x arrow sign y holds, where x intersect y equals phi, it is said to be a completely non-trivial fd. Normalization. If a database design is not perfect, it may contain anomalies, which are like a bad dream for any database administrator. Managing a database with anomalies is next to impossible. Update anomalies. If data items are scattered and are not linked to each other properly, then it could lead to strange situations. For example, when we try to update one data item, having its copies scattered over several places, a few instances get updated properly, while a few others are left with old values. Such instances leave the database in an inconsistent state. Normalization is a method to remove all these anomalies and bring the database to a consistent state. The Systems Development Lifecycle, or SDLC, also referred to as the Application Development Lifecycle, is a term used in systems engineering, information systems, and software engineering to describe a process for planning, creating, testing, and deploying an information system. The Systems Development Lifecycle concept applies to a range of hardware and software configurations, as a system can be composed of hardware only, software only, or a combination of both. Preliminary analysis. The objective of Phase 1 is to conduct a preliminary analysis, propose alternative solutions, describe costs and benefits, and submit a preliminary plan with recommendations. Conduct the preliminary analysis. In this step, you need to find out the organization's objectives and the nature and scope of the problem under study. Even if a problem refers only to a small segment of the organization itself, you need to find out what the objectives of the organization itself are. Then you need to see how the problem being studied fits in with them. Propose alternative solutions. In digging into the organization's objectives and specific problems, you may have already covered some solutions. Alternate proposals may come from interviewing employees, clients, suppliers, and/or consultants. You can also study what competitors are doing. With this data, you will have three choices: leave the system as is, improve it, or develop a new system. Systems analysis. Requirements definition. Defines project goals into defined functions and operation of the intended application. It is the process of gathering and interpreting facts, diagnosing problems, and recommending improvements to the system. Analyzes end-user information needs, and also removes any inconsistencies and incompleteness in these requirements. A series of steps followed by the developer are: collection of facts. End-user requirements are obtained through documentation, client interviews, observation, and questionnaires. Scrutiny of the existing system. Identify pros and cons of the current system in place, so as to carry forward the pros and avoid the cons in the new system. Analyzing the proposed system. Solutions to the shortcomings in Step 2 are found, and any specific user proposals are used to prepare the specifications. Systems design describes desired features and operations in detail, including screen layouts, business rules, process diagrams, pseudocode, and other documentation. Development. The real code is written here. Integration and testing brings all the pieces together into a special testing environment, then checks for errors, bugs, and interoperability. Acceptance, installation, deployment. The final stage of initial development, where the software is put into production and runs actual business. Maintenance. During the maintenance stage of the SDLC, the system is assessed to ensure it does not become obsolete. This is also where changes are made to initial software. It involves continuous evaluation of the system in terms of its performance. Evaluation. Some companies do not view this as an official stage of the SDLC, while others consider it to be an extension of the maintenance stage, and may be referred to in some circles as post-implementation review. This is where the system that was developed, as well as the entire process, is evaluated. Some of the questions that need to be answered include: does the newly implemented system meet the initial business requirements and objectives? Is the system reliable and fault-tolerant? Does the system function according to the approved functional requirements? In addition to evaluating the software that was released, it is important to assess the effectiveness of the development process. If there are any aspects of the entire process, or certain stages, that management is not satisfied with, this is the time to improve. Evaluation and assessment is a difficult issue. However, the company must reflect on the process and address weaknesses. Disposal. In this phase, plans are developed for discarding system information, hardware, and software in making the transition to a new system. The purpose here is to properly move, archive, discard, or destroy information, hardware, and software that is being replaced in a manner that prevents any possibility of unauthorized disclosure of sensitive data. The disposal activities ensure proper migration to a new system. Particular emphasis is given to proper preservation and archival of data processed by the previous system. All of this should be done in accordance with the organization's security requirements.